Hello and welcome to the presentation of the conference paper in Dynamic Modeling and Agile Control of a Mecanum-wheeled robot. This is the table of contents of the things I will explain during this presentation. First, I will give a small introduction to the problem. Then, the model of the system will be explained. Afterwards, the controller design will be explained and 3 test cases will demonstrate its effectiveness. Finally, a small conclusion will be given. As an introduction, I will briefly explain what omni-wheel robots are. These are robots that, as their name suggests, use omnidirectional wheels to move. These are wheels that have rollers attached to their rims, as you can see on these images. A robot equipped with this can move and rotate freely, in all directions, without having to do complicated maneuvers. This is an advantage in tight spaces with flat surfaces, which is why they are used a lot in the manufacturing industry. In this schematic, we see how, when applying a motor torque to the wheel indicated by the green arrow, the rollers let the wheel slide in one direction, the black arrows, which then forces the ground reactions felt by the wheel to be in the perpendicular directions, the red arrows. In this figure, we see how an omni-wheel robot can use its wheels to move to the right. The motors apply the green torques to the wheel, which then generate red ground reactions on the robot. We can see that the vertical components of these reactions cancel each other out, while the horizontal components add up to a horizontal ground reaction to the right. It is important to note that while the vertical components cancel each other out, they still require the motor to exert additional torque, and therefore are wasting energy. Omni-wheeled robots are usually controlled using simple kinematic models, which are not able to account for this wasted energy. Therefore, the objective of this paper is to design a motion controller that is able to minimize energy consumption in this type of robots. This controller will need to be able to navigate to a certain goal state based on a full dynamic model of the robot and its actuators. It also needs to be flexible enough to avoid obstacles and sudden changes in the environment. Modeling of the motors will let the controller respect the voltage limits and minimize their energy consumption. To construct the controller, we first need to define the model of the robot and its actuators. The configuration of the robot, QR, is defined by the position X, Y, and orientation psi of the robot relative to a world frame, while the configuration of the wheels, QW, can be defined by the turning angle of each wheel, phi1 to phi4. The full configuration Q of the robot is then obtained by stacking these two vectors. We note that while QR and QW can take any value, their time derivatives are not independent from each other. They are coupled by a kinematic constraint. Using the standard kinematic equations for omni-wheel robots, we get a constraint that relates the velocity of the wheels with the velocity of the robot, where R is a matrix which only depends on the robot dimensions, and R psi is a rotation matrix that depends on the orientation of the robot. This equation can be rewritten as a kinematic constraint on the full configuration vector. It can be shown that this constraint is not integrable into a constraint on Q only, so the robot is a non-holonomic system. Therefore, to find the dynamic model of the robot, we will need to use Lagrange's equations with multipliers. To do so, we first need to write the kinetic and potential energies of the robot in terms of the configuration variables, and then differentiate them. As the system is non-holonomic, we need to add the kinematic constraint by using the Lagrange multipliers. The Lagrange equations result in a set of complex expressions which can be condensed into a single expression that only depends on QR, as you can see on screen. Here, the H matrix is the mass matrix of the robot, and thus depends on the masses and moments of inertia of the different parts of the robot. K is the generalized Coriolis matrix, which depends only on the angular velocity of the robot. and Fa is the generalized force of actuation, which depends on the torques acting on each wheel, tau1 to tau4. As we mentioned previously, we want to model the motors in order to be able to minimize their energy consumption. Therefore, we need to find an expression to get the torque acting on each wheel in terms of the voltage of each motor and the state of the wheel. The torque acting on each wheel is the torque produced by the motor minus the torque lost due to friction. The motor torque is based on simple DC motor equations and the information found on the motor datasheet. The friction has been modeled using dynamic and static friction, the values of which were found experimentally. The next step is to design the controller. First, we formally define the needs of the controller. We need to be able to find the future states and their corresponding inputs, which minimize an objective function. The future states are constrained by an initial condition. They are also linked together by a state transition function. Finally, we can add inequalities to further restrict some variables in the controller. The objective function is defined as a weighted sum of different objectives. We minimize the distance to the objective to help the robot reach its goal. The energy consumed by each motor is also added to the objective function, with a smaller weight so that the controller minimizes it. The state transition function is defined by discretizing the dynamic model using the explicit range-QTA method of fourth order. The inequalities are set up to adhere to the voltage limits of the motors, make the robot stay within the workspace, and avoid obstacles. The controller was implemented in MATLAB using the Forces ProSolver, which uses an internal point method to solve nonlinear model predictive control problems. A visual interface was created, where the simulation and controller run in real time. The current robot position is shown in gray, and the plan is shown as a pink line. The goal of the controller is shown in blue. A series of test cases were designed to test the controller. In the first test case, the robot moves freely from one position to the next. This video shows how it performs the movement. It is interesting to see how, even though the goal is at an angle, the robot first moves horizontally. After a while, we can also see that the robot starts to rotate before going to the goal, and it does so in a diagonal fashion. These behaviors can be explained by studying the forces on the robot. When moving horizontally, the total force is greater, so it makes sense to accelerate horizontally. However, as we mentioned at the beginning, this also causes some energy to be lost in the form of competing forces. Therefore, once the system has finished accelerating, it is best to move diagonally in order to avoid this energy loss. The second test case introduces some obstacles for the robot to avoid. We can see how the obstacles are avoided successfully, even when the gaps are too small for the robot to go sideways. The robot manages to turn around and go through the gap, using its smallest side. The third and final test case introduces moving obstacles. This poses a challenge for the controller, as it will have to recompute its plans every time an obstacle moves unexpectedly. Nonetheless, the controller still manages to reach the goal. To conclude, we have shown that a model predictive controller can be used to design an agile and energy-efficient controller for Mecanum-wheeled robots. The controller constructed takes into account the full nonlinear dynamics of the robot and its actuators, and manages to get usable results in real time. While the test scenarios only show static goals, they could also be made time-varying. Also, the controller could be used as a local planner if embedded into a higher-level global planner.